All right, so we have talked about the differential rate law. So these videos are all going to focus on the integrated rate law, which looks at how concentration changes over time. So we are going to do a few things. We're going to talk about the relationship between concentration and rate for each of these orders. And we're going to look at the graph that makes a linear graph for each of our relationship, for each of our orders of reaction. And we're going to use that graph to derive the integrated rate law equation. And then we're going to use our integrated rate law equation to derive our half-life equation. And we're also going to talk about the units for the K value for each order of reaction. And remember that K is the rate constant. So the first order we're going to talk about is negative order. Now, in terms of negative order, we're just really going to talk about how it affects the rate. So if it's negative order, it actually hinders a reaction. So not necessarily stops the reaction from occurring, but it slows the reaction down. All right, if I have a zero order rate law, it means that this species has no effect on the rate. So what you may see in your rate law expression is that they write the concentration of that species to the zero order, or sometimes they just leave it out of the rate law expression. Okay, so in this case, when we graph and get a linear line, we're graphing the concentration. So we should know that these brackets represent concentration versus time. And time varies on the reaction. Time could have units of minutes, time could have units of seconds. All right, so the integrated rate law equation is based upon the equation of the line. So we know that this is y is equal to mx plus b. All right, so the y-axis is concentration, okay, and that would be at some period of time. M is the slope, and we can see that this has a negative slope, and the slope is equal to our rate constant k. X is time, and again, time can be in minutes or seconds. And B would be the y-intercept, so the place where we intercept the y-axis is the concentration of A, and this little zero here means initial, so it's the initial concentration of your species. All right, so that is our integrated rate law equation for zero order. Now, from the integrated rate law equation, we can derive the half-life equation. Now, since this is the first time we're talking about half-life, we should probably define half-life. So half-life is the time required for a reactant to reach half its original concentration. And if you don't like the word original, think of initial. Okay, so I'm going to rewrite our integrated rate law equation and then show you how from that we derive the half-life equation. All right, so if we're talking about half-life, then our concentration is going to be half the original. And I want to do some movement around of our equation. First of all, I would like us to move this kt to the other side, because by doing so, then we get rid of our negative sign. And then that means, so let's do that move first. So then we have kt plus my initial over 2 equals. Now, eventually what we want is we want t by itself so that we know the half-life. All right, so we're going to have to move this initial concentration of A divided by 2 to the other side. Now, it's a fraction, so we need to make the other side a fraction. So this is like 1 times A initial. So I'm going to just make these 2 and 2. And then when I move to the other side, I now have kt is equal to, because 2 minus 1 is 1 on the top, and then the halves stay. All right, and then we're going to want t by itself, so we're going to divide both sides by k here. And so my half-life time is A initial over 2k. So this is our half-life equation. Now, you won't need to derive half equations on the test or on the quiz, but you'll need to know the equations for the test and for the quiz so that we can solve problems. We're actually going to do problem solving at the end once we've covered all the orders of reactions. Okay, and then the last thing we need to talk about is K. So if what I said earlier is true, that this has no effect on the rate, then this means that the K would have units that match the rate. So this would be moles per liters times seconds. Because remember, this moles per liter is molarity. So it's molarity per second. All right, those are our notes for zero order, and also our notes for a negative order of reaction.